The Life and Discoveries of Archimedes by Rohan Sagar and Madeline Keller. Rohan and I figured it would be interesting to learn more about the discovery and formation of the math we used every day this year in 4th period AP BC calculus. And when we learned that Archimedes was the first person to approximate a value for pi, a value that we worked with almost daily in class, we knew our project had to be about him. Although he lived a long time ago, the formulas and theories that he invented were hugely influential on the worlds of both physics and mathematics, and many remain valid to this day.
Archimedes was born in 287 BCE in the city of Syracuse in Sicily, Italy. He was killed in around 212 or 211 BCE during the conquest of Syracuse. He was killed by a Roman soldier. When he was buried, on his tomb, he had carved a sphere within a cylinder, which represented how he solved the formula for the volume of a sphere, which he believed was his greatest accomplishment in life. His father, Phidias, was a mathematician and astronomer, and Archimedes followed in his footsteps and went beyond that by being a mathematician, an astronomer, a physicist, an engineer, an inventor, and a weapons designer. Many of the discoveries that Archimedes made involved King Hiero II. He frequently asked Archimedes to handle real-life problems that he had, which often led to mathematical discoveries, such as Archimedes' screw, the concept of measuring volume by displacement, and many others. One instance of Archimedes working for the king is the story of the Archimedes screw. King Hiero couldn't empty rainwater from one of his ships, so he'd asked Archimedes for help. Archimedes came up with an idea to use a machine that would bring the water from the ship outside, going from low to high. He came up with the idea to use a machine that was a hollow tube with a spiral inside that would be turned by handle. When the spiral moves, it would bring the water from inside the ship, from a low point, to outside the ship, from a high point. This spiral is used in many developing countries as a way of irrigation and is still used today. Another discovery he made while working for the king was discovering volume by water displacement. The king had given gold to a goldsmith to make him a crown, and when the goldsmith gave the crown back, the king wanted to make sure that he hadn't stole any gold for himself, so he weighed the crown to make sure it weighed the same amount as the gold that he'd given at the start. And after weighing, the crown did weigh the same, but he was still skeptical, so he asked Archimedes to figure out if the crown was pure gold or not. While pondering the situation, Archimedes was taking a bath, and as he got in, he realized that as he submerged, the bath overflowed, and this gave him the idea of volume by water displacement, which means that the volume of water displaced is equal to the volume of the object that is submerged in the water. After figuring this out, after calculating the volume of the crown using water displacement, he found the density of the crown by dividing the mass of the crown by the volume. He compared the density to the density of pure gold and concluded that the crown was a mix of silver and gold. While this was troubling news for the king, it was a great discovery for science and for learning. Other discoveries that Archimedes made were finding the volume of a sphere. He considered this to be his greatest accomplishment, and he had how he found the volume of a sphere. He had that carved onto his tomb when he died. He also came up with a surface area of a sphere, and we'll get into the volume and surface area. We'll get into that part later. He also came up with the physical law of buoyancy. Buoyancy is the ability of an object to float in a liquid, or in other words, the liquid can exert an upward force great enough to keep the object from sinking. A solid object in a liquid will experience an upward or buoyant force, that is the same magnitude as the weight of the liquid that is displaced by the solid. The volume of the liquid that is displaced is equal to the volume of the solid that is submerged. He also came up with the formula to find volume of a sphere, which he considers his greatest accomplishment. And for somebody as accomplished as Archimedes, that's saying something. Since a sphere doesn't have any edges to take measurements from, Archimedes had to think creatively of a way to grasp how to find the volume of it. His first step was to cut the sphere in half and make two hemispheres. He would then take the volume of one of these hemispheres and double it to get the volume of the sphere. A hemisphere is easier to work with because it has a flat side, which makes it easier to take a measurement from. His next step was imagining that hemisphere inside of a cylinder with the same radius as the hemisphere and with a height equal to the radius as well. Doing that, it put the hemisphere perfectly inside of the cylinder. His next step were to take slices, starting at the top of the cylinder where the hemisphere was the smallest. This was similar to taking slices and how we do with integral calculus, which we spent a bulk of the year on. To think that Archimedes had almost come up with integral calculus 1800 years before it was actually invented by Isaac Newton is unbelievable. The only difference is that he didn't take slices infinitely small, but still the same concept and very impressive. Archimedes took slices going all the way down until the final slice where the cross-section of the cylinder and the bottom of the hemisphere were the same. Archimedes was interested in the difference in the cross-sectional area of the cylinder and that of the hemisphere. If we look at the graphic, the blue is the difference between the cylinder and the hemisphere. So when you start with the first slice, the hemisphere is almost infinitely small. There's not much to take off. So it's basically just the cross-section of the cylinder. As you move down, the cross-section of the hemisphere slowly gets bigger and bigger and bigger until finally, in the final slice, they are the same. Now, taking these cross-sectional areas, he multiplied that by the depth of each slice. Now, with those volumes that he just found, those ended up adding up to the volume of a cone with the same radius as a cylinder. The volume of a cylinder, the equation for the volume of a cylinder, is already known as pi r squared h. Same with the cone, which is already known as 1/3 pi r squared h. Archimedes realized that to find the volume of the hemisphere, you had to subtract those two, which would give you 2/3 pi r squared h. But in this scenario, h equals r. So it's really 2/3 pi r cubed. And as we stated before, a sphere is double the volume of a hemisphere, and that's how Archimedes came up with the volume for a sphere as 4/3 pi r cubed. He also used this logic to figure out the surface area for a sphere as 4 pi r squared. More discoveries that Archimedes made was creating a place value system of notation with a base of 100 million. While he wasn't the first to come up with a place value system, he had no idea of the Babylonian place value system that had been made before he discovered his. So technically he still had an original idea, which he pursued and made possible. He also was able to determine the apparent diameter of the sun. He did this because, going back to the place value system, the whole reason he needed the place value system was because he needed a way to represent a number large enough that it could represent the number of grains of sand it would take to fill up the entire universe. And to figure out how much that would be, he had to know the size of the universe. He decided to take the Aristarchus heliocentric model of the universe to do his calculations. In order to do what he needed to know the circumference of the Earth, the relative sizes of the Earth, Sun, and Moon, and the apparent diameter of the sun. Many of these values had already been calculated by other scientists and philosophers and astronomers. However, Archimedes decided that he wanted to come up with the diameter of the sun on his own. He decided for the other values that he would just use what his predecessors had came up with. To do this, he directed a straight rod towards the sun, almost like a telescope. And then he put his eye at one end and a cylinder at the other. He looked through with his eye at the cylinder and placed it so that it completely covered the sun to get an upper estimate for the diameter. Then he moved the cylinder so that while looking, there was a little bit of sun visible at either side for the lower estimate. To find the diameter of the sun, he would use the radius of the cylinder and divide it by the distance from the cylinder at the upper and lower estimates from his eye. But he knew that his eye wasn't just seen from a point, it was also seen from an angle. So he made appropriate corrections for these measurements and was able to find the appropriate values. He doesn't specify how exactly he gets these angles, but he does say that when finding his results, determining how many times the angles are found inside a right triangle is that the larger angle is smaller than 1/164th part of a right triangle, and that the other smaller angle is larger than the 1/200th part of a right triangle. And what all of that means is that he had found the apparent diameter of the sun to be between 27 degrees and 32 degrees and 56 minutes. The values that we use today vary by the time of year, but they range from 31 degrees and 3 minutes to 32 degrees and 35 minutes. So basically, Archimedes had come up with a range that was correct for any time of year. Let's just take a minute to comprehend what he was able to do here. He used a rod and a cylinder, and using complex mathematics, he was able to determine the apparent diameter of the sun. The sun is over 90 million miles away, and looking at it for too long can blind you if you aren't wearing proper eye protection. Archimedes was able to estimate a value of something so far away and so big, and with minimal technology. And it was more than accurate, as we see by the values used today, and comparing that to what he'd come up with. Archimedes had also found an approximation for pi. As we've seen in the past, Archimedes was intrigued by calculating values for curved solids, like the cylinders and spheres and cones and everything that we've talked about to this point. So he wanted to learn more about pi. Pi is the ratio of a circle's circumference to its diameter, and it is used in many formulas. Archimedes knew that the circumference of a circle was equal to 2 pi r. So to find pi, he found the circumference of a circle with a known radius and then solved for pi. He used a method called exhaustion. Now to start off, he imagined a circle with an equilateral triangle inscribed and circumscribed about the circle. Looking at this graphic here, we can see how the shapes, while there isn't a triangle, you can see how the shapes are both inscribed and circumscribed. And he does this with shapes going all the way up to 96 sides. He figured that finding the perimeters of polygons with straight edges would be easier than finding the circumference, which you would need to know what pi is. So he started off with a triangle, and he found the perimeter of the one circumscribed, which would be greater than the circumference of the circle, and he found the perimeter of the one inscribed, which would be less than the circumference of the circle. And what he does next is similar to the squeeze theorem, which we learned this year, in which he gradually brings the upper and lower limits closer to one number, and what's left in between is this circumference of the circle. Using a formula that he had developed earlier, he's able to find the perimeter of a polygon with twice the amount of sides as the previous one. So, after the triangle, he uses a hexagon, one inscribed and one circumscribed, and he has the perimeter of each one. And he's able to limit down what the circumference of the circle should actually be like. He does this process over and over again until he gets to a 96-sided polygon, which is essentially a circle unless you really want to zoom in and see the slight differences from what it actually would look like. Now, doing his calculations, he was able to estimate that pi had to be somewhere above 25,344 over 8,069 and less than 29,376 divided by 9,347. Now, later on, these two values were simplified to 3 1071sts and 3 1/7. Back to this. Using the two values we found before, he averaged those and evaluated pi to be 3.141868115 to 9 decimal places. And his value to 9 decimal places differs by less than 1 part in the 10,000s from the pi that we use on our calculators. We chose to use a pi as our trinket because it is one of Archimedes' greatest discoveries, and also because we used pi in most of the units we did this year, and it's an essential part in calculus, especially volume by rotation, which uses slices. What else has slices? A pie. So, we decided to make a pie. Also, sadly this year, our last day of school was the day before Pi Day. It's tragic that we couldn't experience that day in class. Otherwise, we could have passed this pie around and all had a great day. But for now, here's our virtual pie.
This is me making the chocolate peanut butter pie for our project. I first melted 4 tablespoons of butter in the microwave and crushed up 25 dark chocolate Oreos in our food processor to make the crust. Once the butter was melted and the Oreos were crushed up, I mixed them together in this metal bowl, and then I poured that mixture into the pie pan. I then pushed all the crumbs firmly into the edge of the pan so that when the pie was cut, the crust would not fall apart. And once that was done, I put the crust in the oven for 5 minutes at 350 degrees so that the crust could set. Then I started to work on the filling. I used the mixer to blend all the ingredients together. The first ingredient I put in was 8 ounces of cream cheese, and then I opened up a new bag of powdered sugar to get 1 1/4 cup of powdered sugar, and then I got 1 cup of peanut butter, and I used a whole tub of Cool Whip. I then blended all these ingredients together in the mixer, which took a little bit to make sure that everything was mixed together and there were no lumps or bumps. I then took a break from recording so that the crust could cool off before I put in the filling. I dumped most of the filling into the pan and began to spread it around with a spatula, and then added in little bits as I needed to. I spread it all out to the edges and made sure to get a nice and even filling of the pie. Once I used up as much of the filling as I could, the pie was done.
Well, there's our trinket of a pie. We wish we could have shared that in class, but it is what it is. Some fun facts about Archimedes are that he actually made war machines. One of his most famous ones was the Claw of Archimedes. Kind of like the crane game, you could pick ships out of the water, move them around however you wanted to, and sink them. Easy as that. Also, he invented the phrase eureka. This goes back to our story about him in the bath and discovering how to use water displacement to find volume. Supposedly, he jumped out of the bath after his discovery and shouted eureka, and then continued to run around the city naked yelling Eureka. Also, it's possible that Archimedes was related to King Hiero. Plutarch wrote that the two were related in his Parallel Lives, a series of biographies that he wrote. And since a lot of Archimedes' stories involve the king, it is a possibility that the two could have been related. Maybe Archimedes was royalty. Also, Archimedes invented the first odometer thousands of years before the first car was made. It was a little cart that you pushed around, and it would drop a ball into a container after every mile. And lastly, his last words were said to have been, "Don't disturb my circles." Well, that was it. Thank you for watching. Have a great day.